Good day, everybody. Today, I want to cover a topic that's been getting increasingly larger amounts of attention, and it's referred to as machine learning explainability. And it involves being able to explain certain black box properties of models after they have been trained. So we all know by now that machine learning models can oftentimes act as some sort of black box where the users have almost no insight into how the model arrives at a particular decisions or how it's making decisions in general. What the field of explainable AI allows us to do is understand why a model is giving us a certain prediction and give us insight into why it's behaving the way that it's behaving. Now, there's a couple of approaches we can take when we're faced with this problem. So the first one is the most specific approach, and that is providing local explanations. So if the model makes a prediction for a specific example, we can use local explainability techniques to understand why the model has given us that exact prediction. Then we have global explanations. And here we're looking at the average across all predictions that the model is giving us. And this is going to give us an idea about the model's decision making process in general. And then we have cohort explanations, which is a little bit of a combination of the above two. And it is when we get an average across a subset of data. Now you might be asking, why is this important? And it involves two main reasons, I would say. And one is to increase the trust of business and all of the users that are going to use this model and trust its predictions. And also, there is an increased call for regulation in the AI industry. And regulators might request us to explain the model and explain why certain predictions were given. So one approach to solve this problem would be to develop models which are inherently interpretable. And we already know that some models are more of a black box than others. So you might want to end up using something like linear regression with very few features to give business an understanding of exactly how the model makes its predictions. The drawback of this, obviously, is that usually the more interpretable a model is, the less accurate this model becomes. And it would be very helpful if we could find a way where we could benefit by using a model that's more accurate and having some techniques to peek inside this black box. So today I'd like to illustrate a technique that allows us to gain insight into a model and provide some explainability and not compromise on the accuracy of the model that you're using. So with this technique, you can go and explain something very complex like a neural network, and have the benefits of a model with very good performance, very high accuracy, but at the same time being able to explain how the model arrives at its decisions. So we'll first need to import all the packages as usual, which you require when you start a new machine learning project. And the second part will be to train the model. And here, this is exactly what I do. I fit a scikit-learn linear regression model on the data, and I then have a regression which I can use for future predictions. So this piece of code here is used to generate all the coefficients of every single feature, and as you can see, this was the resulting model that got trained on the data. Now, linear regression models, as I've mentioned before, are quite interpretable, and this is very easy for someone like a business user to understand, where they're aware of what all the features mean in the business context, and they understand the direction as well as the size of the coefficients of all the variables in this linear equation. So the first method that I will explain, which will help us to understand the mechanisms of the trained model better, is called permutation importance. Now, to give some intuition behind what exactly this technique will tell us, I will just say that permutation importance is used to evaluate the importance of every feature in your model after the model is trained. So the steps involved in it at a very high level will be to take a specific column, so take a specific feature, then randomly shuffle these features, or randomly shuffle the values in this feature, and then take your model, generate a prediction for each of these data points with the shuffled features, and then compare that new score against the original score. So once you've calculated that, you can then calculate the drop in the score, and this will give you the importance. So scikit-learn does have some documentation on that that describes it. And here you can see I have some code to generate a permutation importance plot. It's quite simple. So you import permutation importance from scikit-learn, and then you give this function your regressor, your model, your data points, and after you've run it, then you can generate a plot like this, which will give you insight into which features are the most important for your model's accuracy. So this is the first method that I want to discuss. But then there's another method, and this is called partial dependence. So you'll have an original data set, and then you'll artificially set a feature value to an X value. So in this example, we set 80 to 0, and then you predict the value for each artificial row. Once you've done that, you can get the average of all those predictions and then repeat for a different value of X on that specific feature. So the end result of something like this would be what you'll see here, and it'll have it'll investigate a specific feature. Here we chose the first column in the data set, and it'll plot the predicted values or the average predicted values for different values or for different artificially generated values. Now, you can clearly see that this gives us an idea of the relationship between the specific feature and the target. And by that, I simply mean that if you're changing the feature by a certain amount, how will that influence the prediction of the target variable? So you might be asking yourself, well, it's great that I know this, but how does the partial dependence plot relate to permutation importance that we spoke of earlier? And that's a very good question. And it's really important to explain this intuition to any business users. So we've already established that some features are more important to maintain accuracy for the model than others. But what does this exactly mean? And I would define this as the following. So let's say you have a specific relationship between the feature in question and the target variable. If that specific feature is not very important, and even if the partial dependence plot shows a specific relationship, it's going to mean that for that feature, we might not always see the trend as indicated on the partial dependence plot. However, if you contrast this with a feature that is very high on the feature importance scale, it becomes much more certain that the relationship in the partial dependence plot is valid. So here we could see that for feature 1, it is clearly very important compared to all the other features. And if we do plot its partial dependence plot, we get a specific relationship. So for this feature in question, we end up looking at the partial dependence plot, looking at this relationship, and having much more certainty that this is the actual way that the target will change given some change in a feature. And that's all that it comes down to, essentially. And I hope it has become clear why both these techniques need to be used if you want to offer a way of explaining the inner workings of a model.